Han is a physics PhD candidate at the University of Arizona, and he has a broad interest in diverse theoretical and experimental topics of continuous variable quantum photonics. He designed an experiment that fabricated and tested the photonic chips for generating the on-chip squeezed light. And now he is working on the application of quantum sensing and quantum communication, and aims to investigate their quantum advantage. And let's welcome Han.
Hi, everyone. Can everyone see my slides right now?
Yeah.
Oh, okay, cool. Yeah. Okay, so it's been a great pleasure to be here to share my recently posted theoretical paper on arXiv. Yeah, so if you're interested in the detail of the paper, feel free to check it out, or we can discuss later. Yeah. Yeah, so before we start, I would like to give a brief introduction to myself. So my name is Han Wu, and I'm currently a PhD candidate in the University of Arizona in the US. And in 2011 and 2014, I respectively completed my bachelor degree in National Jiaotong University and my master degree in National Tsinghua University in Ide Yu's lab. From 2015 to 2017, I joined Yin-Chen Chen's research group in Institute of Atomic Molecular Sciences as a research assistant. Since 2017, I started pursuing my PhD study in the University of Arizona and was advised by Dr. Zhesheng Zhang, who is now the associate professor in University of Michigan, and co-advised by Dr. Chuntao Zhuang, who is now the assistant professor in USC. And now I'm going to graduate in the end of this year. And this seminar, I will talk about our proposed quantum radar for identifying the direction of a distant unknown object. And I will demonstrate the quantum advantage comparing with the classical counterpart. Yeah, so I was informed that this talk will within 1 hour. So I only got like 16 slides, include the thanks and acknowledge slides. So it looks like we have plenty of time. So feel free to stop me if you got confused, or yeah, feel free to ask me any questions. Feel free to stop me. Yeah, so here's the outline. So the outline, so in the beginning, I will give a very brief introduction of the basics of quantum optics. Well, just very brief. And after that, I will talk about the frameworks of our classical and quantum radar scheme. And afterwards, I will introduce the lower bounds of the estimator to quantify the evaluation performances. So the first lower bound I would talk about is the Kramerov bound, which is very well known in metrology. And the second lower bound I will talk about is a zigzag bound, which I will introduce later. Yeah, and then after that, I will evaluate the Kramerov bounds and zigzag bounds of the formation classical and quantum radar schemes. And I will explore the quantum advantage with experimentally feasible parameters. And finally, I will give a conclusion. So as we know in classical electrodynamics, the EM field is a wave caused by the oscillation of its electric field and magnetic field. And the information of the EM field is carried by the energy quanta, we call photon. With the emergence of quantum theory, people are thinking about to apply this theory on the EM field. So to make sure that everyone understand when I say quantum or classical, I will give a definition. So to differentiate the classical optics and quantum optics, I will make the definitions first. So the classical EM field is defined as the field that is fully characterized by Maxwell equation and short noise theory. And specifically, the fields that is generated from the source, a coherent source like laser, or coherent source like laser, or some sources like thermal or vacuums. All these kind of sources are classical. And the photons of these classical fields are uncorrelated with each other in terms of any degree of freedom, because their source of generation is in thermal equilibrium with the environment. Okay, so this is how we call classical. So basically, if you read a lot of the quantum optics papers, they say, okay, this is classical. It means most of the time they say, okay, they use a coherent light like a laser. Yeah. Okay, so but what is quantum field? So quantum EM field is defined as the field generated via some nonlinear interactions. And the generated photons, as you can see, these photon pairs have some quantum mechanical correlation. And this quantum mechanical correlation is beyond the interpretation of classical theory. And you can think of it, this entanglement comes from the preservation of the energy conservation and momentum conservation law. So this generating photons pairs are entangled in some degree of freedom. And this degree of freedom is determined by the types of nonlinear interaction. So depending on the discrete or continuous degrees of freedom of the entangled photons, it can be generally characterized as two variable cases. So the first one is called discrete variable quantum information, and the second one is continuous variable quantum information. So for example, in discrete variable, the generated photon pairs are entangled in polarization domain. As we know that in free space optics, the polarization could be like a vertical polarization or horizontal polarization, that they are discrete. And in continuous variable, so the generated photons are entangled in quadrature domain. So if you're not familiar with what is quadrants, you can think of it like a phase and amplitude. So because we know the photon is actually an EM field, so it has the amplitude and phase. And phase and amplitude, they are all continuous. So that's why we call it continuous variable. And most of the time, in general, in quantum metrology, people are dealing with the continuous variable. So in the following, I will give two well-known applications that exploited continuous variable quantum light to perform quantum metrology. Okay, so the first is a very well-known LIGO, the department. So yeah, we know that LIGO won the Nobel Prize in 2017. And the team of LIGO utilized a non-classical light source to boost the sensitivity of the gravitational wave measurement. As you can see that in the right lower figure, see that you can think of it like the vertical axis as the noise flow. And you can see that if the LIGO team used the non-squeeze light, it shows like this very spiky curves, the red spiky curves. But if they use the squeeze light, which is a non-classical, like you can think of it like a non-classical light, yeah, it gives you a better sensitivity. The noise flow will be lower. Yeah, so this is one example that quantum metrology can be used to detect the gravitational wave with better better performance, better results. Another example is the distributed quantum sensing. So imagine that you fabricate or you build up a quantum circuit. So these circuits are composed of different like beam splitters to split the beams, and to a bunch of beam splitters, like kind of stuff. So and the quantum circuit has n+1 inputs, and what the quantum circuit does is that it makes all the modes with a linear combination. It's a very, you have to specially design your quantum circuit. But anyway, it's a n+1 linear combination. So you can even, if you mathematically, you can write it as a matrix. Yeah. So in the input port, you inject a quantum light. You inject an entangled light in quantum light from one port, and leave the rest ports to be vacuum. So basically, you don't shoot anything there. Okay, so the quantum circuit will distribute the signal from one port to the rest, right? And there are also n+1 outputs of this quantum circuit. So in the output port, you just do a bunch of displacement operations and homodynamic measurement on each arm. Okay, so if you don't know the detail about like the displacement operation or homodynamic, but basically it's just a process. Yeah. So if you have done so, you basically create a multi-partite entangled state. So you create the multi-partite entangled state. So the mean square error scaling, if you inject this quantum circuit with the entangled light, the quantum circuit has the scaling, mean square error scaling as 1/m squared. But if you inject your circuit with a coherent light, which we call classical, in that case, you only get 1/m scaling. So probably you're confused, like, why? How come it will be different? Because in coherent light, all the modes, even though you have a quantum circuit, you mix all the input ports, but they are coherent states. So the coherent state as an input, they are still uncorrelated, even though you mix them up. But if for entangled lights will be different. If you mix the entangled light with other ports, you basically entangle all of them. So if you entangle more modes, you have better sensitivity. And the scaling for quantum case is better than the classical case. And for the classical case, you can derive this scaling as, you can think of it like a random walk. You get the same scaling result. Yeah, so this paper was theoretically published. Yeah, and also was experimentally realized in recent years by our group members. Yeah, so this is also another quantum metrology that use continuous variable. Okay, so let's talk about our framework. So in classical radar framework, let me recap a little bit. So the classical, I mean, you send the light in a coherent state, okay, coherent source. And so let's say your target is an unmanned aircraft system on the sky, or any unknown object on the sky, which is very far away from your transmitter. And you want to transmit the coherent state, coherent light, coherent microwave to the target. And then on the ground, you prepare 2 receivers. And then so to be noticed, the coherent source is a high time bandwidth product pulse, which I will explain why we use a high time bandwidth product pulse. Yeah, so this pulse will shoot from the transmitter to the target and will be reflected to the receiver 1 and 2. Okay, so because we use a microwave and the object is very far away, so when the transmitted photon hits the target, the reflected wave will be like a spherical. So in receiver 1 and receiver 2, the 2 beams that arrives with 2 receivers, they are approximately parallel. So let's say the theta is the reflected ray with the vertical direction with theta. So if you determine the theta, you can determine where the unmanned aircraft system is, right? So basically, if you want to interrogate what the direction of the target is, you basically just need you are interrogate like what is this theta. Okay, so this is a coherent state radar case. I think everyone knows it. Okay, but remember we use a microwave pulse. So in microwave domain, so the overall channel will be very noisy. The mean photon number of the environment is very noisy. And since that the target is very far away, so the overall transmission, which is I use a kappa, is very, very small. So the overall channel, you can think of it like a very lossy and noisy channel. Okay, so in quantum radar case, basically they are all the same, except that the transmitter transmit the entangled photon, not the coherent state. Okay, so here the transmitter. So there are pre-shared entangled photons between receiver and the transmitter. So the receiver keeps an entangled photon, one of the entangled photon in a quantum memory, just store it. Okay, and the transmitter has the other entangled photon. So the transmitter, we do the same thing, send the transmitter to the target and reflect it back and receive by two receivers. So the two receivers receive the two, so now receiver has two photons, right? So what the receivers need to do is just do the joint measurement. Yeah. So yeah, this is the quantum radar framework. So basically, we just replace the coherent light by this entangled light. So I'll explain like why we use microwave pulse with high bandwidth product. So imagine that if you use a transform limited pulse. So let's say this pulse has is not chirped. Okay, so you can the delta omega times delta TD. TD is the duration of the pulse, and delta omega is the bandwidth. If this field is transform limited, the delta omega and TD has a relation, which is the multiply this two equals to 2 pi. So the SNR is proportional to the peak. P is the peak power times the duration time, TD. So if, in general, when we do metrology, of course, we want the SNR to be as high as possible. But if you use a transform limited pulse, given that the P is a constant, if you want to have high SNR, the TD has to be high. But in that case, the minimum time scale is also high. So that means your resolution is bad. So we use a high time bandwidth product. So in that case, the delta omega times TD is much greater than 2 pi. Okay, so TD and delta omega, they don't form a correlation. I mean, in this case, yeah. So the minimum time scale, if you use a high time bandwidth product, it could be very small because the minimum time scale is 2 pi over delta omega. So which is it can be much smaller than TD. So the reason why we use a high time bandwidth product, because we want to make sure that SNR can be as high as possible and the resolution can be as small as possible. And this transform limited prohibits you doing that, but high time bandwidth product allows you to do so. So that's why the microwave, we choose a microwave pulse as a high time bandwidth product. Okay, so let's talk about the estimator's bound. So if we want to estimate something, so for example, if you want to do some measurement, you need to have a system role, and the system is interacting with another system to be tested. And the interaction between the two systems is characterized by an unknown parameter, theta. So our goal is to estimate the theta. So we need to do the measurement. Okay, so when you do the measurement, you basically got a bunch of outcomes, right? And you have the probability densities. If you have you have so many trials, and you can get, okay, this probability density will be like a Gaussian, or yeah, like a Gaussian, yeah. And then based on the probability density with the outcomes, you estimate the theta check. Okay, the theta check is to estimate what is the value of theta. And we can prove that the Kramer bound is that if you want to make sure that this theta check is good enough, we want to make sure that the mean square error between theta check minus theta, this mean square error, is as small as possible. But the Kramer bound sets a limit. So this cannot be 0. It has to be greater or equal to this Kramer bound. And this Kramer bound can be calculated by the inverse of Fisher information. Yeah, I think everyone, a lot of people probably must have heard about this Fisher information. So the Fisher information, basically you can just use the probability density, take the log and derivative, yeah, and take the expectation value to get it. Yeah, so this is it sets the limits of your the minimum accessible data. Yeah. So, but it seems like, okay, this Cranberry bound would be a good, right? It would be a suitable measure to evaluate the performance of the measurement, because like a quantum case, you have a Cranberry bound. In classical case, you have a Cranberry bound. You can just compare them, right? So everything should be fine. Well, actually, in reality, this is not going to happen, because this Cranberry bound is not tight enough. So if you want to remember here, I said you need to get a probability density, but the probability density depends on the x, which is your outcomes, and the theta. So you need to have almost infinite amount of outcomes. You need to have infinite trials to get this probability density. But if you don't have infinite trials, you only say like, let's try like 100 times. Maybe it's not large enough. So if you plug in this Cranberry bound, you plug in this formula to calculate this Cranberry bound, you underestimate the achievable errors. It's too low. Yeah, so you need an alternative bound. So this is another bound, Zip-Zakai bound. So basically, you need a rho. You have interaction with the system to be tested, with the interaction determined by the unknown parameter theta and do the measurement. But so far, it's the same as the Cranberry bound case. But here, it's a different thing. So Zip-Zakai bound, in Zip-Zakai bound, we take the full advantage of a prior knowledge for the measurement outcomes that relates to the MSE of a mean square error to a binary hypothesis testing problem. So what do I mean is that you don't need to do like infinite trials. You only need to do like 2. So for example, in this case, so let's say you have the prior knowledge for the outcome. So the scenario will be different. So you have some prior knowledge for approximately like what is the probability of what is the probability that you can get X, and what is the probability that you can get X plus tau. Okay, so let's say the incident that happens that your result is X. I call it hypothesis 1, H1. If you get a result which is X plus tau, I call this hypothesis 2. So in Zip-Zakai bound, you can prove that this is tighter, it's greater than Cranberry bound. And yeah, you can see that it's a very, this double integral, there are some formula, there are some derivations here, but I want to skip that. But you can see that this Zip-Zakai bound takes the full advantage of the prior knowledge, which is px and px plus tau. And the PE here, the PE here is the minimum error probability, which means that if you want to calculate the Zip-Zakai bound, you need to tell the difference. What is the minimum error probability that you can get between H1 and H2? So error probability, I mean like, okay, you get the result X, but it turns out it is X plus tau. Yeah, or if you got X plus tau, but it turns out it's X. Yeah, so this is what I mean error probability. So you want to minimize it. So let's assume that the prior knowledge for this, your hypothesis testing problem, the Px is a window function. So which means that you can see that the red rectangular curve, it has a deviation, uncertainty, delta phi. So the delta phi is the prior knowledge uncertainty. Yeah. So you can see that the calculation is the mean of a px and px plus tau. So basically, this gives you the dash red this black dash curve. But anyway, this is the detail. But yeah, so you need to have this minimum error probability, and px and px plus tau is all given. It's a prior knowledge, and then you just need to plug in this minimum error probability. Okay, so how do we get this error probability, minimum error probability? In classical case, which means you send a coherent line. Yeah, sure.
We have a question here.
Yeah,
Sure.
what's the condition that you will have this prior knowledge? Because all this information is nature.
Could you repeat again? Sorry, maybe it's a little bit far, so I can.
So in what situation that you can get all this prior information?
Oh, you mean how do I get this prior knowledge?
Yeah, yeah, because
Yeah. Good point. Yeah. So the prior knowledge is just you use another way to. So you mean? I know why you're confused. Yeah. So basically, you have another way to do the measurement, but the measurement outcome is just it's not precise enough. But you get the prior knowledge it's not completely unknown. It's you know something, but it's kind of not that precise. So basically, you can use coherent state to do. What I want to say is, you have other ways to. So what? Okay, here I use quantum light to boost the sensitivity, and I will prove that the quantum result will be better than the classical one, right? So this is okay, but there are a lot of ways that you can get access to, like approximately like what would that be. So you can just use coherent, like just coherent, like just classical radar case. You can get some idea about what is the px. So here is just a theoretical paper. So I assume that within this delta phi window, you have some probability. You have some well, it's not it's probability density. Probably I shouldn't say probability. Yeah, you have some knowledge about this px. You have some knowledge about px plus tau, and this is. So how do you get this prior knowledge? Is you use other ways to get access of that information. It's just you have the uncertain delta phi, which is not that precise. Yeah. So does that answer your question?
Yeah, because what I confused is that once you understand all this probability, you just use the error propagation, then you can definitely understand what's the error of your estimate.
You mean error propagation? Yeah, but I think that part in that case will be another thing, and also all the propagation. Well, okay, so here I want to prove that the quantum light, all you do the propagation, all the error propagation thing, you use classical, right? So the number of trials, the more that you trial, you have better result. But in quantum case, the scaling will be better. Does that make sense? So like this thing. So the classical, the more trial that you get, of course you have better result. The MSC scaling is lower, but the quantum case you give it even 1/m², it drops even faster. So yeah, even though of course you can use like other ways to estimate the results, yeah, but it's not the point that I want to mention. I want to say quantum is better than classical if you use quantum light. Yeah. Okay. Yeah. No problem. Okay, so here I just assume like a px and px plus tau as a window function, and then I will, do some simulation and see how it goes. Okay.
Sorry,
Yeah, sure. Yeah.
Sorry.
No, yeah, you ask your question, right?
I want to ask, what's the difference for classical and quantum case here? Is that the information we know about the P, the probability?
No. So far it's not. So the only difference is this row. Whether this row is an entangled state row or a coherent state row.
Where is the row here?
Row here is your system. For example, your microwave pulse. Your microwave pulse is in coherent state. You can write it as a density operator.
Yes.
So this row is the classical or quantum.
But this will determine Px and P.
No. Px and P. No. That's totally different. So this Px and Px plus tau is you have some prior knowledge. If you want
Okay,
to ask how do you know this PX? It's a prior knowledge. You have so many ways to know this prior knowledge. Yeah, but the quantum and classical case, the only difference is this rho. In classical case, this rho is a coherent state. In quantum, it's an entangled state, or in our case, it's two-mode squeezed vacuum state.
Okay, so the prior knowledge of P are they related to the measurement resolution?
No, it's it's a prior knowledge. So I mean, resolution. Yeah, you can think of it like a resolution that you can think of it like you use other system, other ways, not this quantum or other ways to measure it, and then you get some prior knowledge. Yeah, and
Okay.
of course, this prior knowledge, this uncertainty will be limited by the resolution of, the other way that you do the measurement. Yeah, that's for sure. That's why you have a delta phi uncertainty here, because you don't know for sure. Like in our case, I assume that within this range, it's flat. But yeah, so you can think of it, this delta phi is the resolution.
Okay, great. Thank you. I see.
Yeah. So how do we get this error probability, minimum error probability? So in classical case, you can just use a maximum likelihood estimation. Okay. So, but in quantum case, it's called Hellstrom limit. So whether it's in classical or quantum case, you basically need to calculate this formula, which is very complicated. So you can think of it like this x so the incident x has a corresponding density operator rho x, and the hypothesis 2 x plus tau has a corresponding density operator rho x plus tau. So if you want to make sure that the error probability is the smallest, you need to make sure that the overlap between the two density operators are the smallest, right? If they are completely, they have no overlap between these two density operators, and then of course you can completely separate them, so the error probability will be 0. But it doesn't work that way. So you need to calculate the distance between the density operators. But how do you calculate a density operator's difference, which is is not an easy task. Yeah, so you can see that this norm 1 is defined by the trace of the square root of rho Dagger rho. Yeah, so it's very difficult to calculate it. So if this error probability in classical case, it's very easy, but in quantum case, it's hard. Okay, so if you just calculate this, plug in this error probability to this Div-Zakheim formula, in quantum case, there will be a disaster. I don't know how to calculate it. It's too difficult, especially you see that there are two double integrals. Yeah, but we know that this Hellstrom limit is upper bounded by a quantum Chernoff bound. Okay, so yeah, this quantum Chernoff bound is not sure whether you guys heard of quantum illumination. So that when in quantum illumination, it's very similar to here. So you have hypothesis 1 that the target is present. Your hypothesis 2 that the present is absent. You need to tell like the minimum error probability that whether this target is there or whether the target is not there. You need to calculate the error probability. Okay, so that is lower bounded by this quantum Chernoff bound. Yeah, so the Hellstrom limit is lower. In our case, it's the same. So we want to plug in this Hellstrom limit or minimum error probability by this quantum Chernoff bound. Okay. So here, so when I say that, do you guys have any problem about this? So what I want to do in this slide is that, in general, I just calculate. Yeah.
Also, question about what the ZZB means.
zip-zag bound. Sorry, probably I should have a zip-zag bound. Yeah, zip-zag bound. It's the same formula that I use here, zip-zag bound. Yeah, I just copy paste. It's the same formula. And now, right now, I replace this PE by quantum Chernobog bound, PQ. So probably you might confuse like why the greater the you see that this delta theta squared ZZB is greater than this much. Oh, sorry, probably here I wrong a little bit wrongly. So this should be the whole formula is the zip-zag bound. I'm sorry, I shouldn't wrote it in this way. Yeah. So yeah. So okay. Yeah. Okay, let's move on. So okay. So what I define is Kramerov bound, and what I talk about like a zip-zag bound. Now I would like to use apply these two bounds to the quantum and classical scenarios that I mentioned. Okay, so here is the result. The CZZB is the classical zip-zag bound, which you can see is hold on a sec. Oops. You guys don't see my mouse, right? Okay, anyway. Yeah, so the red solid curve is the classical zip-zag bound. And the blue solid with a green dash curve is a quantum zip-zag bound. And you can see that, oh, sorry, I should mention, the y-axis is your result. It's your calculation, the minimum variance, the minimum delta phi that you can get, normalized to this delta phi square reference. So this delta phi square reference is the zip-zag bound by assuming a random choice. So PEX plus tau, I set it to be 1/2. Okay, so you just randomly guess whether it is X or X plus tau. Okay, so you can see that the quantum zip-zag bound is always lower than the classical zip-zag bound. Yeah, and the red dot line is the classical Kramerov bound, and the blue dotted line is the quantum Kramerov bound. You can see that the zip-zag bound is always greater than the Kramerov bound. Oh, I should mention here earlier. If you want to observe the quantum advantage, what I mean quantum advantage is that classical zip-zag bound or classical Kramerov bound is always lower than the classical counterparts. You need to assume that the mean photon number of your pulse is much less than 1. Yeah. So I made this approximation here. So you can see that, and the x-axis is the SNR. So you can see that if the SNR, the signal to noise ratio, is very low, you basically this delta phi square normalized to delta phi reference is 0. So it makes sense, right? So if the signal to noise ratio is very, very low, you are just random guessing X and X plus tau. You can tell the difference because the SNR is very slow. I mean, it's very low, yeah.
I have a question about could you remind me how does signal to noise ratio take part into the box?
I'm sorry. Say again.
Could you remind me that how do this signal to noise ratio take part into this bump?
Oh, signal to noise ratio. I didn't write it, but it's sorry. Yeah. Signal to noise ratio is basically it's n mean photon number times the transmissivity divided by MB, which is the environment mean photon number times the time bandwidth product. So I didn't write down, but it relates to your mean photon number, your channel, the kappa, the channel transmissivity, your environmental mean photon number MB, and also it depends on your time bandwidth product, which is the mode of your Is
that kind of prior information that we
No,
No,
it's not the
so
prior. It's not the prior information.
could you back to the slide
Sure.
that you have? Yeah. The bound.
This one? Oh,
The
you mean
expression.
the archive bound? Here.
Yeah. So from
Okay.
here, how does this information of the signal to noise ratio in we're connected in SNR here?
SNR signal to noise ratio is it depends on your it's nothing. So what you're so are you confused about like where does it come from, right?
Yeah. Because
so it comes from the row. It comes from the row because the mean photon number you have the light. So whether the mean photon number is large or small, if the mean photon number of the light is large, you have better signal to noise ratio. You can think of it like you have greater power. Think of it like this way.
Okay, so that comes from our initial preparation state.
Yeah.
Okay.
It's nothing to do with here. It's
Okay.
what signal to noise ratio is rho and rho theta, this part.
Okay, so there's nothing to do with the measurement.
It has nothing to do with the measurement. Yeah.
Okay, I see. Thank you.
Yeah, once you determine the channel, you got the transmissivity of the channel. You got the MB. MB, I mean the environmental mean photon number, and your mean photon number for your pulse. Yeah, and you can just calculate it. Yeah. Yeah, no problem. Yeah. Okay, so this is the result. So to quantify the quantum advantage, we define the quantum advantage as the most significant contrast between QZZB and CZZB. So basically, it's the difference between these two. Okay, and the corresponding signal to noise ratio threshold, we call it SNRTH. Okay, so if the SNR goes to this much, you have the most striking, the best quantum advantage. Okay, so I make this definition. So here I set the SNR to be the threshold, SNRTH, to be like some number. In this case, it's 4.88. But of course, this depends on the bandwidth, like delta omega and MB, and a lot of stuff. And what is your central wavelengths? Yeah, so I don't want to talk too much about it. Yeah, but anyway, I send this SNR to be the threshold so that we can have the greatest quantum advantage, and I tune the range, which is how far the object is, and the pulse duration here as the x-axis. So this is a density plot. You can see that clearly there's a boundary thing. So in this boundary, it will be like a 12 dB quantum advantage. And you can see that even in, so if the range, so if it goes upward, the range is lower. That means the object is far away from your transmitter. Your transmissivity decreases, right? Yeah, it makes sense because it's even far, so transmitted is slower. So that's why the quantum advantage drops. It decreases. Yeah, it makes sense. What about the NS? In this case, if you increase the pulse duration, you basically, while setting the SNR to be equal number, some number, the NS, the mean photon number of your pulse decreases. So remember that I said that if the NS is very small, the quantum case is better than the classical case. You have much less error probability. Yeah, so you have better. You have better. I would say have better result. Yeah, so that's why when NS goes higher, duration goes higher, NS goes higher, NS decreases, but the quantum advantage increases because in NS is very small, quantum advantage is more significant. Yeah. Okay. So this is basically the last slide. So here is the take-home message. So first of all, we show that we yeah, the zip-Daka bound is the tighter bound than the Kramerov bound. Consider the number of trials are finite. Okay. And second, the sensitivity of the pulse compression radar outperforms the classical counterpart. And finally, the appreciable quantum advantage can be achieved with experimental feasible physical parameters. So what I mean is that if the pulse duration could be like a 0.1 second, like 0.1 seconds, if the range is within like 600 meters, you can still have the quantum advantage like 12 dB. Yeah. So yeah, of course, in real, I'm a friend that because it's a theory paper, so I discussed with my friend. We deal with the microwave experiments. So this is what they told me, like the coherence time for the, if you want to do like a very long coherence time microwave, it should be very hard, but for 0.1, it should be fine. So if you make sure that the duration is only like a 0.1 seconds and within the coherence time, yeah, you should have this quantum advantage within, if the range is within the 600. Yeah. Okay. Yeah. So I will acknowledge the Dr. Saika Guha. He's a professor now in College of Optical Science in our school, and Dr. Chuntao Zhuang is my co-advisor in Department of Electrical and Computer Engineering, and now he moves to ESC. Yeah. Also, we acknowledge the funding source, the National Science Foundation, and Raytheon. Yeah. Okay. So, any question?
We have a question here.
Sure.
Can you hear me?
Yeah.
Okay. So my question is, in deriving these bounds, does the entanglement play the role in those bounds? How do you find their effect there?
Sorry. Can you say again? I don't
I
really
mean,
understand.
in the quantum case, are we using the entangled photon? If that's
Yes.
the case, how's the entanglement coming to the bounds?
It's the rho here, the rho density operator. So the entangled photons, the rho will be different from the coherent state rho. The rho will be different. So you calculate the error probability will be different. I didn't say how do I calculate the quantum Chernow bound. You can see that there are like rho x times rho x plus tau, and you take the trace. It's a very complicated calculation process. But for entangled and coherent, the difference is the rho. The rho of coherent states rho is different from the entangled photons rho.
For entangled photon, the density matrix will be twice larger, right?
Well, usually because it's a Gaussian state here, right? So we use a two-mode squeeze vacuum, which is Gaussian, and coherent state is also a Gaussian state. So in general, we don't explicitly write down the rho. We use covariance matrix. So if you have there are some papers talk about from covariance matrix, how do you calculate this quantum Chernow bound? You don't really need to calculate this rho. You calculate the covariance matrix of coherent state and entangled two-mode squeeze vacuum state, entangled states. Yeah. So what you are saying is like, okay, yeah. So covariance matrix for a coherent state will be like a 2x2 matrix. Yeah. For a two-mode squeeze vacuum state, it's a 4x4. But in our case, it's even harder because it's a 3-mode case. It's not a 2-mode because you see you have 2 receivers. So it's a 6x6 covariance matrix. Yeah.
Yes. Okay. I see. And so, sorry, I just want to check. You say the Gaussian state is for quantum or for classical?
No. Gaussian is just the Wigner function. It's like a Gaussian state. It doesn't say it's a classical or quantum. So coherent state, the Wigner function is a Gaussian, right? But for a two-mode squeeze vacuum state, its Wigner function is also is also Gaussian. It's just not symmetric. It's like an elliptic shape. So it's also Gaussian. So when I say, so if it's any Gaussian state can be characterized by the covariance matrix. But that's the detailed thing. Well, what I'm saying is that the Gaussian, there are two concepts. Gaussian state is saying that the Wigner function is like a Gaussian state shape, whether it's symmetric or asymmetric. Yeah. But quantum and classical is telling, classical is more like whether you have, classical is that you don't have correlation, the photon, or a covariance matrix, the off-diagonal turn is 0. You can think of it that way. The off-diagonal turn of the coherent state is 0. So that means there is no correlation. Yeah.
I see. So you mean either quantum or classical, if they are kind of Gaussian, you can calculate them in the covariant matrix. That's the point?
Yes.
Okay.
Yes. Any Gaussian state can be characterized by covariant matrix and the mean photon and the mean value. But the two Moskowitz vacuum, the mean is 0. So only covariance matrix is enough. But for coherent state, you need a covariance matrix, which is identity 1, 1, 1, 0, 0, 1, identity matrix, and then the mean value. It gives you the Wigner function. Yeah.
So sorry, what gives the Wigner function?
So if you want to calculate the Wigner function of a coherent state, you need the covariance matrix and the mean value of your quadrature.
Okay, I see.
Yeah.
So one more question. Why the ZZB bound is an upper bound? It comes from the Chernoff bound. So what is that? Why they give the upper bound, not the lower bound?
It's like, you can think of it like, because Kramer bound, you just randomly, you don't have any prior knowledge. You just take data, right? Take the data. What you did is just take the data. So you don't have any prior knowledge. But Zip-Zakai down is different. You sort of have some prior knowledge, like what is the probability density that you will get for X? What is the probability density for you can get X plus tau? So of course you should have better result. You should. So like I said, these two scenarios are different. For one, it's just you don't have any knowledge. You just take data. What you do is take data. For here, it's more than just take data. You take data, but you have some prior knowledge about what is the probability density for the data that you take. So of course, it has better result. Oh, you mean like why it is upper? So upper bound. I mean, it's greater than. You mean why it is? Why it is greater than the Kramer bound? Because the Kramer bound, you have basically infinite trials. So, yeah. Sorry, second. Yeah, you keep going.
So you mean upper bound means any experiment you do, the estimated delta theta cannot be far away from the true theta than the upper bound. So that's what you mean. So that's because it's limited by the prior information, so it cannot be further away. So that's what you basically mean.
Sorry, I don't understand. Can you say it again? Yeah.
Okay. Never mind. I'm just curious. You just say the prior knowledge will limit the range of the difference of the theta. Okay.
Yeah. What I want to say is it's tighter. So if you want to, so let's say this delta theta square, you say, okay, it's lower bounded by this delta Kramer bound. You think that, oh, okay, Kramer bound, let's say give you a number like a 0.1. You say, oh, so that means I can get 0.12, right? I can get 0.13. But the truth is you will never get 0.12 or 0.913 because you take only finite value. You have only finite trials of measurement. But in Zip-Zakai bound, yeah, in deep dark bound is different. You have some prior knowledge, so it's tighter. It's yeah, it's tighter. Yeah, it's you know what I'm saying. So it's you can get like you Cranberry bound underestimate because you must try infinite times. You underestimate the minimum error. Yeah.
So are you saying that if we have time and resource that we can go to have infinite trial, then Cranberry bound will be equivalent to ZDB?
Good point. You see that here, the train is similar, but in classical case, they are still a little bit different. But in quantum case, yeah, you see that these two, when SNR goes to very high, SNR goes too high, you can think of it like infinite trial. SNR goes too high, it means infinite trial. We see that the quantum is close to, it is in quantum case, deep dark bound merges with the quantum Cranberry bound. But these two are totally different estimation methods. So I won't say like when SNR goes to very high. So because there are two different methods to estimate this thing. So there are papers to prove that Cranberry bound is tighter than the deep dark. Deep dark bound is tighter than the Cranberry bound.
Hi, I have a question. So
Sure.
could you go back to the slide which you have like one transmitter and two receiver?
Sure.
The entangled state case. Yeah. So I was wondering, so in here you say you have this transmitter, it will have prepare some entangled states and sending half the entangled pair to the sensing, and then the receiver will receive the reflected entangled pair. So in this case, then does it matter whether like which two entangled? How can I say? Like receiver, we have two receivers. So does it matter like which two pair? Which two like? So I have one of them like each they receive one photon, but I was wondering like which like the received photon is corresponding to which the photon in the transmitter is. Does that matter or something?
Oh, I think I got what you're saying. So you're saying that maybe the one receiver receive a photon, but receiver two doesn't have. Is that what you're saying?
Yeah, maybe that will happen. Yeah.
Yeah. So this is a continuous variable case. In continuous variable, the light is continuous wave. I mean, it sends always. Well, not a continuous wave, it's a pulse, but you sense the light always. So it's not like I know it's saying you like the photon, a single photon detector, right? So you say okay, you count one photon, but here it's not the case. The light is always sending. It never stops.
Okay.
The pulse is always sending, so you always have photon. So this is the difference between discrete variable and continuous variable. For discrete variable, you care about like polarization encoded in a single photon level. Like you have a one photon or you don't have photon. But in continuous variable case, the light is, it's not photon number counting. It's the light is always sending.
Okay.
And what you do, the quantum measurement in continuous variable case, you do the homodyne, which is another story. But it's they're different. It's not like a one photon thing. It's the photon is always there. There are so many photons because light is continuously sending the microwave.
Okay, so
you always have photons.
So the two receivers, like the thing they received is just some difference in the path, like because
Yeah. Sorry, probably in this slide I forgot to mention. Yeah, so you basically detect the time of flight, the difference of the time of flight, which in this case d sine theta, right? So d sine theta divided by c speed of light is basically the time of flight. difference. I mean, time of flight difference. So you measure that time of flight difference. So the time of flight difference has the theta inside, right? D sine theta divided by C. So the theta is inside that sign. So you know the information of theta is embedded in the time of flight difference. So you can just measure. Yes.
I'll just explain a little bit more. Like, so I know this. Maybe there's this path difference. Then what can I infer? Well, what do I know about this thing?
You mean path difference? I mean not like this symmetric way or any way, right?
I was just wondering, like, then in this case, what thing do I measure exactly?
What you need to measure is the signal. So you do the homodyne, which I didn't mention here. I'm saying that so the transmitter transmits one entangled photon, and then reflect it back to the receiver one and receiver two. And receiver one and receiver two, they perform a joint measurement. That joint measurement, you have like a lot of receiver can like a conjugate variable receiver or OPA receiver. There's another story, but you can design how do you receive your photon? Yeah, that's another story. Yeah, I didn't mention it here. I just say I receive it and then it's a theory paper. But yeah, you in detail you probably need to like how do you receive it? There are like a conjugate variable receiver or OPA receiver. Yeah.
Okay.
Yeah.
Thank you.
That's a detail thing. Yeah.
Sorry, I have a follow-up question for this.
Sure.
And in the case that two receivers all receive the photons, and how do we think of them? I mean, plus the transmitter, are we thinking in total 3 photons entangle, or we just think two photons?
No. Probably I put a photon here. You might a little bit confused. What I'm saying, so for here is continuous variable. It's always mode, not photons itself. So it's not like it's the 3 modes they are entangled, not 3 photons are entangled. So one mode consists infinite numbers of photons. Probably I put a circle there. You saw like is this photon is entangled with another one. It's a misunderstanding. It's not a photon itself entangled with another. It's a continuous variable. So the light is always sending there. So there are so many photons. So what we define in continuous variable is mode. You can think of it like the direction. Like the transmitter here is a mode, and receiver one is another mode. Receiver two is another mode.
So it's 3 more entangled.
So 3 modes are entangled. Yes, exactly. There's a 3 mode entangled state, not a 2 mode entangled. 3 mode entangled.
And this mode entangled will like compensate the flight difference, because the mode will include all the time information. Is that correct? Because
the mode include time information.
Because receiver one and receiver two will have the time difference to receive the mode, right?
Yes.
So
that's theta. That's theta. Theta is not. I mean, theta. You can think of it. Okay, theta is everything that you measure is a distribution. Theta. Let's say theta is the real theta. I mean, the real angle that you want to measure. Theta is just the mean value. What I'm checking the performance is the variance of the distribution. Does that make sense? So this theta is just a mean value of your distribution. But what I want to do is I want to make sure that the variance of your measurement is as small as possible. I'm not saying that this theta is which number. I just make sure, because you always have the variance.
I see.
Because it's a field, it's light field. It's a time, time distribution. It always has distribution. You cannot send a direct delta function pulse, right? I mean, in that case, in frequency domain, you have wideband. But anyway, Yeah, I'm saying that what I'm doing is I want to make sure that the variance of measuring this data is as small as possible.
I see. Okay.
Yeah.
Sorry, I understand this, but maybe I go back to the previous upper bound question again.
Sure. Yeah, of course.
My question is the ZZB comes from the prior knowledge,
Yes.
which give you another bound, which is larger than the Kramer lower bound.
Yes.
And for the ZZB, I mean, it tells you the difference of delta theta, right? So it should be another information about the theta must be at least this amount. So I think it's another lower bound for delta theta, not the upper bound. That's my question. Do you understand my
sorry. Can you say again? I don't quite understand.
Okay, say for example, you have finite measurement, say just one measurement or two measurements. So you will give you you will tell you the difference will be very large. So you can say that your difference is the delta theta will be at least this bound, at least this amount, which is given by ZZB. So it should be another lower bound for delta theta. Not that. That's my understanding. So I'm just confused. Why is upper bound?
Oh, you mean why it is greater than this Kramer lower bound?
No. I forget about the Kramer lower bound. I'm just saying ZZB, why it give you the bound, it give you a bound of delta theta, and it give you the bound, tell you the delta theta must be larger than ZZB or lower than ZZB. That's my question. Forget about
maybe you're asking like, how do I end up this formula? Like why delta theta is, if you have a prior knowledge, why this delta theta is greater than like this ZZB?
Yeah, probably. Yeah, this question. And this are these related to how many measurements you do here?
Just two, x and x plus tau.
Or just two measurements?
You need to make sure. Yeah, just two. We don't need infinite trials. Yeah. You said why it is lower? Yeah.
And so the first inequality, delta theta is greater than delta theta ZZB. So this actually give you a lower bound of delta theta, right? Just
yeah. So six theta ZZB is the lower bound.
Oh yeah, that now I understand. Just the ZZB is larger than Kramer lower bound, but they both give you the lower bound of delta theta.
Yeah. You can think of it like, if you want to estimate something, you cannot 100% make sure, okay, this is here, so delta theta is 0. You cannot do that, right? Because everything is distribution. What you send the light is a distribution. So you always have some overlap. If you want to say x and x plus tau, there are two distributions extending from -infinity to infinity. So there must be some overlap. But just overlap could be very small.
I see.
Yeah. So it cannot be 0. You must have some bound. It cannot be 0. But the point is, how did you measure it? How do you estimate it? It gives you like the value of this bound. But it cannot be 0. Yes.
Okay, great. Thank you. Very clear.
Yeah, no problem. Yeah.
Is there any further questions? Okay, if there's no further question, thanks for speaker again.
Thank you for no problem. Yeah, thanks for inviting me. Yeah, if you have any more question or we want to discuss more, just feel free to email me.